Good day everyone. In today's video, we're going to talk about the second major category of oscillator, which is the relaxation oscillator. So relaxation oscillator is a second type of oscillator that uses RC timing circuit to generate a waveform that is generally a square wave or other non-sinusoidal waveform. Typically, a relaxation oscillator uses a switch trigger or other device that changes states to alternately charge and discharge a capacitor through a resistor. So the relaxation oscillator contains energy storing devices like capacitor and inductor. These devices are charged by a source and discharged through a load. The shape of the output waveform of the relaxation oscillator depends on the time constant of the circuit. So let's understand the working of the relaxation oscillator with an example. So here, a capacitor is connected between a bulb and a battery. This circuit is also known as the flasher circuit or RC relaxation oscillator. In here, a battery charges the capacitor through the resistor. And during charging of the capacitor, the bulb remains in off condition. When the capacitor reaches its threshold value, it discharges through the bulb. Thus, during discharging of the capacitor, the bulb is glowing. So when the capacitor is discharged, it starts charging by the source again and the bulb remains off. So the process of charging and discharging the capacitor is continuous and periodic. So the charging time of the capacitor determines the time by the time constant, and the time constant depends on the value of the resistor and capacitor for the RC circuit. Therefore, the flashing rate of the bulb decides by the value of the resistor and capacitor. The waveform across the bulb are as shown in the figure below. So next is the triangular wave oscillator. A triangular wave oscillator is a type of oscillator that generates a positive and negative going ramps when the dual polarity switch is thrown back and forth at fixed intervals, which creates a shape of triangular waveform. The basic idea of triangular wave oscillator is illustrated in figure 1627a, where a dual polarity switch input is used. When the switch is in position 1, the negative voltage is applied, and the output is a positive going ramp. When the switch is thrown into position 2, a negative going ramp is produced. If the switch is thrown back and forth at fixed intervals, the output is a triangular wave consisting of alternating positive going and negative going ramps as shown in figure 1627b. So next is a practical triangular wave oscillator. In practical triangular wave oscillator, the output of comparator circuit is a square wave having constant positive and negative levels. The square wave at the input generates triangular wave at the output of integrator circuit. The upper trigger point and the lower trigger point determine the type of switching for comparator, and more than one output periodic waveforms are present in the circuit, and hence the name function generator is also applicable for this circuit. One practical implementation of triangular wave oscillator utilizes an op-amp comparator with hysteresis to perform the switching function, as shown in 1628. The operation is as follows. To begin, assume that the output voltage of the comparator is at its maximum negative level. This output is connected to the inverting input of the integrator through producing a positive going ramp on the output of the integrator. When the ramp voltage reaches the upper trigger point, the comparator switches to its maximum positive level. This positive level causes the integrator ramp to change to a negative going direction. The ramp continues in this direction until the lower trigger point of the comparator is reached. At this point, the comparator output switches back to the maximum negative level and the cycle repeats. This action is illustrated in figure 1629.
So now we report about output voltage controlled oscillator. So first we have our table of contents, sawtooth controlled oscillator, VCO, POT programmable unijunction transistor, and a square wave oscillator. So first, the voltage controlled oscillator is a relaxation oscillator whose frequency can be changed by a variable DC controlled voltage. One way to build the sawtooth VCO is with an op-amp integrator that uses a switching device, PUT, in parallel with a feedback capacitor. So PUT is a programmable unijunction transistor with the anode, a cathode, and a gate terminal. The gate is always biased positively with respect to the cathode. When the anode voltage exceeds the gate, a voltage by approximately 0.7 volts, the PUT turns on and acts as a forward biased diode. When the anode voltage falls below this level, the PUT turns off. Also, the current must be above the holding value to maintain conduction. The operation of the sawtooth VCO begins with the negative DC voltage. V in produces a positive going ramp on the output. So this is our two diagram. So first is the initially the capacitor charges, the output ramp begins when the PUT is off. So the capacitor rapid diagram. So first is the initially the capacitor charges, the output ramp begins when the PUT is off. So the capacitor rapidly discharges when the PUT momentarily turns on, hence creating our sawtooth voltage diagram or graph. So a transistor that can be triggered into conduction when the voltage at the anode exceeds voltage at the gate. The gate can be set to the desired sawtooth voltage. PUT triggers on when the output ramp exceeds. It turns off when then the capacitor begins to charge, generating a new output ramp. The frequency of oscillation is determined by the time constant of the integrator and the peak voltage set by the PUT. So this is our example problem. So find the amplitude frequency, the sawtooth output, and sketch the output waveform. So for our solution, first we must find the gate voltage in order to establish the approximate voltage at which the PUT turns on. So we have R4 divided by the summation of R3 plus R4 times the volts. So 10 over 20 times 15 equals to 7.5 volts. So now we have the voltage sets the approximate maximum peak value of the sawtooth output, neglecting the 0.7 volts. The minimum peak value low point is 1 volt. So the peak to peak amplitude is we'll just subtract our um, sawtooth output voltage and our minimum peak value. So we'll have 6.5 volts. Then determine the frequency as follows. So following our equation earlier, we'll have 628 hertz. So in order for us to have our graph, we have to determine the period. So time is equals to 1 over frequency. Our frequency is 628 hertz, and solving it will have 1.59 ms. So a square wave oscillator is the basic square wave um, oscillator shown in 1634, so the diagram beside it is a type of relaxation oscillator because its operation is based on the charging and discharging of a capacitor. This action continues repeatedly and a square wave output voltage is obtained. So that's all for my report. Thank you.
Good day to each and everyone. Now, I will be talking about a stable operation on a 555 timer. A 555 timer connected to operation in the stable mode as a free-running relaxation oscillator. The stable configuration generates an ongoing stream of pulses of fixed length and frequency. It's called a stable since it has no stable state, continually toggling back and forth, meaning our LED is blinking. Like for example, our radio towers. When you in on radio towers, we see a blinking light on top, so aircraft can see the tower when they are passing by in order to avoid any accidents. So here in our figure, um, in our figure, We have three important pins in a stable operation, which is pin 2, the trigger pin, which turns on the output when the voltage supplied to it drops below one-third of VCC. The pin 6, which is the threshold, turns off the output when the voltage supplied to it reaches above two-thirds VCC. And pin 7, which is the discharge. When the output voltage is low, it discharges C1 to ground. So next. Here we have an example. So we have here R1, R2, R3, and C1. R1 and R2 has 4.7 kilo ohm resistor, and we have R3 1 kilo ohm resistor. So for the LED, so the LED will not burn out when connected to our VCC. Then we have our C1 100 microfarad capacitor. So in order to compute the time our LED is turned on, I will use this formula. T on equals to 69 times C1 times R1 plus R2. So using this formula, we get our, on T on, we get 6.486 seconds. And T off, we get 3.243 seconds. The values of R1, R2, and C1 affects the speed of the blinking. Larger values will make the LED blink slower, while smaller values will make the LED blink faster. Meaning, when we change our R1 or R2 to higher values, it will make T on last longer. And if we change our R2 or R1 lower, it will make our LED blink slower. So next slide. Monostable operation. In short, when we say monostable operation, it is a one-shot type of circuit where it is functioning used with a button. When we press a button, the LED turns on, and I will elaborate it in the next slide. So it is considered a timer because it can output pulses of electrical current for exact amounts of time. For example, it could be used to turn on an LED of exactly 5 seconds after a button is pressed. Or it can also make an LED blink on and off or generate higher frequency pulses that will make sound when connected to a speaker. So next slide. So here is a diagram of our monostable operation. So here are the pins of our 555 timer, which is pin 1, which is the ground connected to 0 volts. Pin 2, the trigger pin, turns on the output when the voltage supplied to it drops below one-third of VCC. Pin 3, the output pin, outputs up to 200 milliamp of current at about 1.5 volts. Pin 4, the reset pin, resets the timing operation of the output when it is connected to ground. So here, our reset pin is connected to our positive, so it will not reset. And pin 5, the control pin, controls timing output independently of the RC circuit. When the voltage supplied to it is above 2/3 VCC, when it is not in use, it is usually connected to ground via a 0.01 microfarad capacitor to prevent fluctuations in timings of the RC circuit. Then we have pin 6, the threshold, turns off the output when the voltage supplied to it reaches above two-thirds VCC. Pin 7, the discharge. When the output is low, it discharges the capacitor in the RC circuit to ground. And pin 8, VCC, which is the supply voltage that can range from 4.5 volts to 15 volts. So next slide. Here we have an example. So here is the diagram of our 555 timer connected to all the resistors and capacitors. So we have here our resistor 1, resistor 2, which is 10 kilo ohms, resistor 3, which is 470 kilo ohms, used for the LED, so it will not burn out. Then C1, which is 470 microfarad, and C2, which is connected to our control pin. So the capacitor will prevent fluctuations in the timing RC circuit. So in order to compute the time, it will be turned on or off. We will use this formula. So here it is already inputted. So 1.1 times 10,000 ohm resistor times 0.000047 microfarad or 470 microfarad. After computing this formula, we will get 5.17 seconds. When the button is pressed, the voltage at the trigger pin drops low. When the trigger pin voltage is low, the output pin turns on. At the same time, the discharge pin stops the flow of current from C1 to ground, allowing it to charge. So this is the monostable operation of a 555 timer. Next, we'll have operation as a voltage controlled oscillator using a 555 timer. So here we have a diagram for a voltage controlled oscillator using a 555 timer. Before we use R1, R2 for the 555 timer, now we will add R3 and R4 for our voltage A, which is this. So we have a VCC of 6 volts. So we have VCC times R4 over R3 plus R4 to get the formula for voltage at point A here, which is our voltage controlled oscillator. So when we increase our R4, it will also increase our voltage at point A. And when we increase R3, it will decrease the voltage we have on our point A. So we can use a potentiometer using this is the symbol of a potentiometer. So we can use this to replace R3 and R4. So we will be using the potentiometer. So we will be able to control the frequency so we can output a square wave.